You see, at the end of the last lecture, I was pointing out that all theories in science are tentative, and if you have an intention of becoming a scientist later on in your life, study science and do research in science or teach science, then you must remember this fact that in science nothing is final, everything is tentative. It is as it is today. Today this theory is accepted, tomorrow it might be replaced by an improved theory, or maybe the older theory is thrown out altogether. So, if you are going to be a scientist, you must remember this fact, otherwise you will not be able to do any research. You see, research finds newer theories, newer facts and so on. It cannot if you accept all the facts that are known today. And in addition to that, of course, we had the atomic theory, we reviewed the atomic theory of Dalton and the postulates and the difficulties or the work of various scientists which helped Dalton to formulate those postulates, and then Thomson's plum pudding model, which has the prediction that if I throw a beam of alpha rays on it, then the alpha rays would pass through this with only little deflection. So, let us continue with this. See, my attempt is that along with making you understand the various topics in science, in physics, you must also understand the nature of science, because if you want to become a scientist later on in life, then you must also appreciate the nature of science. And wherever possible, I point out the nature of science itself, the evolution of science. And as I said in the last lecture, all theories are tentative and subject to replacement or improvement with time. So, here is one example. You see, this theory was formulated by Thomson model of atom, and in his model of the atom, the charges are mixed almost uniformly, and therefore, the electric field of the atom would be very small. Therefore, if I have alpha rays thrown on these atoms, they would not be affected much by the electric field of the atoms, and therefore, they would pass with very little deflection. That means, the theory contains within itself the prediction which can reject the theory, and this experiment showed that Thomson model cannot be accepted. So, what happens now? Another scientist, Rutherford, great scientist, he does the same experiment now with the gold foil and so on. This was not the experiment, this is the prediction, this is the experiment, and what he finds is not that the alpha rays are deflected by small angles, but he found that some of the alpha rays are deflected by large angles, and some of them are even bounced, they are reflected backwards, they bounce back as in this case, and most of them go through undeviated. So, these were the observations of Rutherford. So, you can see from these observations that this is not acceptable, because this has not been observed. What has been observed is this, and therefore, the Thomson model of the atom was rejected. And Rutherford, from the results of his experiments, he formulated another model of the atom known as Rutherford's model. And what he said was that at the center of the atom, almost at a point, was the concentration of positive charge. You know, now this is called nucleus. There is a concentration of positive charge and concentration of the whole mass of the atom. And electrons are just orbiting around this, just as the planets do in the solar system. The strong electric field of the positive charge at the center deflected a few alpha particles. A few alpha particles were deflected by large angles because of the strong electric field of the atom, and some of them even bounced back. Some of the alpha particles were found to have bounced back they went like this and came back like this. That means, there was a deflection by a very large angle. So, on the basis of this, he formulated that the atom consists of a nucleus, positively charged nucleus, which is almost a point, and lot of empty space through which alpha rays can go through undeviated, and strong electric field because of the electrons orbiting the positive charge. And this strong electric field deflects alpha rays by large angles, some of the alpha rays by large angles. So, for overall neutrality of the atom, the number of electrons had to be equal to the units of positive charge in the nucleus. So, if the nucleus contains 2 units of positive charge, there must be 2 electrons. If it contains 10 units of positive charge, there must be 10 electrons. So, the atom as a whole was neutral, and this is the model. There is a positive charge here, nucleus, and these electrons are going around it, just like the solar system, where there is sun and planets are going around it. That was the model of Rutherford. And just as in this case, the gravitational field keeps the planets going around the sun, the electric field between the electron and the proton keeps the electron going in orbits. So, this was he was able to explain, but still there is a fatal flaw in the Rutherford model. What is that flaw? You see, if an electron is orbiting in a circular or elliptic orbit, then it is accelerated, centripetal acceleration in circular orbits. So, it is accelerated, and it is known that if electron is accelerated, it must radiate. So, if it radiates, it loses energy, and if it loses energy, it will slowly fall back on the nucleus. So, atom therefore would not be stable. Rutherford model of the atom would not be stable, because of radiation by the accelerated electron. The energy is emitted and electron loses energy and ultimately falls on the nucleus. So, this problem, how to overcome this problem, that was now the question. This problem was overcome by Bohr, and Bohr model of the atom is similar, but with 2 postulates, 2 important postulates. What are those postulates? One, that electrons cannot occupy just any orbit. Electron can occupy only allowed orbits. What are these allowed orbits or stationary orbits? Orbits in which the angular momentum of the orbital motion of electron is equal to n times, n is 1, 2, 3, 4, n times h by 2 pi. That was the first postulate, that in these stationary orbits, Bohr said that the electron does not radiate. Remember, at this moment there was no basis for Bohr to say this. We shall find what the basis is later on, but he made this postulate, and this made the atom stable, because the electron orbiting around the nucleus does not radiate in these stationary or allowed orbits. So, these were the 2 postulates. One, that they are in stationary orbits. Second, that they do not radiate. These orbits are therefore stable orbits, unlike those in the Rutherford model. Orbits satisfying MVR equal to n h by 2 pi are said to be quantized. Now, this word quanti is familiar to you, but at that time this was a new word, quantized, and the integer n associated with an orbit is called the principal quantum number. This n can be 1, 2, 3 is the principal quantum number of that particular orbit. The orbits are also known as shells, like this. The first orbit is K shell, the second is L, and third is M. I think this is well known to you. So, let us not spend too much time on this. The only way in which electron or the atom could radiate is when one electron falls from orbit of higher energy to an orbit of lower energy. The difference delta E is radiated as a photon of frequency nu, so that its energy was equal to h nu. It will also absorb energy, just as it could radiate, it will also absorb energy equal to the difference of any 2 orbits. This any 2 orbits, it could absorb energy corresponding to the difference of energy in the 2 orbits. That means absorbed energy also satisfies the equation delta E equal to h nu. So, once we have accepted to some extent Bohr model, then it is easy now to get radius and energy of an electron in an orbit. So, first of all we will say that electrostatic field between the electron and the proton and the nucleus supplies the necessary centripetal force mv squared by r for the electron to continue moving in that orbit. So, this equation mv squared by r equal to 1 by 4 pi epsilon 0 E times Z e by r squared. Z e is the charge of the nucleus. Z you know is known as the atomic number. For hydrogen it is 1, for helium it is 2 and like that. So, this is the equation that would make electron move in its orbit. So, if we use this condition of stationary orbits mv r equal to n h by 2 pi, h by 2 pi incidentally is known as h cross. It has a value 1.05 10 to the power minus 34 joule seconds. So, h by 2 pi can be replaced by h crossed. So, r therefore, for the nth orbit becomes n squared h crossed square divided by m z e squared, and this k is 1 by 4 pi epsilon 0. Instead of writing every time 4 pi epsilon 0 1 by 4 pi epsilon 0, we shall write 1 by 4 pi epsilon 0 equal to k, which has this value 8.99 into 10 to the power 9 n m square c minus 2, c is for coulomb. So, using these symbols we can write for the nth orbit the radius is given by this, very simple. From this equation of support for the electron to orbit, using the condition of stationary orbits, we can get this. So, the radius of the orbit n equal to 1, this is the radius of the orbit for n. For n equal to 1, it will be h cross squared by k m z d squared. For hydrogen z is also 1. So, we can find its value. For hydrogen, this is known as Bohr radius. For hydrogen atom, the first orbit n equal to 1 is known as Bohr radius, and we can calculate its value. It is 5.29 10 to the power minus 11 meters. I am rushing through this because this is very simple physics. The kinetic energy of the electron is half mv squared, right, and from this mv squared or mv squared by r equal to the electrostatic force, we can use that this one, and we can get E, the energy of the electron, kinetic energy of the electron equal to k z e square by 2 r. Now, electron is in the field of a proton, therefore, it also has potential energy, electric potential energy, and that is minus k z e square by r. So, electron has kinetic energy, it also has the potential energy in every orbit. So, we can sum the two and we can find out the energy in any orbit. If we do that, you find in the nth orbit the energy is minus, remember this sign minus m z square k square E 4 etcetera etcetera. This is the expression for the energy in the nth orbit. It is 1 by n squared. It is proportional to, inversely proportional to the square of the number of the orbit, but it is minus, that is more important. It is minus, this means that the electron is bound to the nucleus. Why? Because I will have to supply this much energy to release this electron from the clasp of the nucleus. Therefore, this negative sign indicates that the electron is bound to the nucleus, just like we are bound to the earth, and if a particle or a body on the earth has to be released from the gravitational field of the earth, you must give it energy so that it has velocity equal to the escape velocity. A similar situation is here. So, a negative sign means that the electron is bound to the nucleus, and we can calculate and we find the energy in the first orbit. That energy is, for hydrogen z is 1 and for the first orbit n is 1, therefore, this energy is minus 13.6 eV. It is actually minus, its magnitude is 13.6 eV, but it is minus. That is the energy of an electron in the first orbit of the hydrogen atom. and it varies as 1 by n squared. So, in the second orbit it would be 1/4 of 13.6, and in the third orbit it would be 1/9 of this. So, this I have shown here. Ground state it is minus 13.6, and this also the first state is known as ground state. The first orbit is known as ground state, and the first then the orbit after that n equal to 2 has energy 1/4 of this. So, minus 3.4 eV. This one n equal to 3 has energy 1/9 of this. So, minus 1.51 eV. You see that this energy is decreasing in magnitude, but since it carries a negative sign, it is actually increasing. You see, minus 4 for example is greater than minus 5, minus 3 is greater than minus 4. So, although the magnitude is decreasing, actually the energy is increasing. That means, the energy of the electron in states n equal to 2, 3, 4, 5 etcetera is actually increasing. That is why these states are known as excited states. They contain more energy, they are known as excited states. So, all these states are excited states, and I have shown also n equal to infinity. You see, you can carry on this and you will see the energy keeps on decreasing, and at n equal to infinity, that means n equal to very large value, E is equal to 0, that the energy with which the electron is bound to the nucleus is 0, is very small. So, it can almost be torn apart at that time. The energy of an electron in the ground state we have already calculated. So, that means we have to give 13.6 electron volts of energy to release an electron in the ground state to pull this electron from the ground state to outside the atom. That means, to ionize hydrogen atom we need energy from the ground state, we need energy equal to 13.6 eV. It is also known as therefore, the ionization energy of hydrogen. Atoms which have only one electron having lost the remaining by ionization or by other means is called a hydrogen like atom. An atom in which there is a nucleus, whatever charge of the nucleus does not matter, but there is one electron around it, that is known as hydrogen like atom. And for example, helium, if it loses one electron by ionization, then it has nucleus and one electron going around it, that is hydrogen like helium. So, for helium, for hydrogen like helium, Z is equal to 2. Therefore, its ground state energy is minus 13.6 Z square, Z is 2. So, it is 54.4, and that is also the energy we must supply to the ionized helium atom to take electron from the ground state. That is, it is the ionization energy of the helium, ionized helium atom. Now, we have already seen that energy is radiated when electron falls from one state to another, from a state of higher energy to a state of lower energy. We have seen that. On the basis of this, the hydrogen spectrum has been classified into various series. So, we shall see in the next lecture what those series are, and then we shall also again look back at the work of Planck, who introduced the idea of quantum of radiation, and then we shall go to the proper topic, the dual nature of matter, the first part of which would be the release of electrons from a metal.